I was recently in India attending the Delhi Sustainable Development Summit. It's a gathering of ministers, heads of state, legislators, scientists, people from the House of Lords, practitioners, United Nations people from both the developed and the developing world. I was inspired by the capacity and the commitment of those people at that conference. It was held about 2 weeks after the Davos meeting. Some of you will know about that one. And the leadership of that particular DSDS meeting made many comments about the fact that Davos was business as usual, whereas DSDS was where the real action began. The takeaway message that I had from that meeting was that many developing nations are well down the track of adjusting to the challenges that we have ahead of us. And we need to ask ourselves, are we, and what will we need to do about it? Now, in the introduction here, the title to this talk, I've implied it's an either-or some of you may have interpreted it that way. But in fact, I hope to argue to you that both conditions apply. That is, business as usual in some respects, and new directions in others. But I need to take that from a perspective that requires a little exploration of context and scale. And that'll be part of the underlying theme throughout the afternoon. So let's begin at the beginning. And this is the longest timescale that we'll be talking about today. That's about 14 billion years or so. And about 4.5 to 5 billion years ago, our solar system formed somewhere in this particular region, you can see here. We were lucky that our planet happens to be formed around about that time at an ideal location in our solar system, a location that allowed life to form and exist. Another time scale. The geologists in our community know this particular timeline very well. 4.5 billion years from here to here. That's where we are now. That's where we began. And these scales here are just subsets of the Phanerozoic and the Cenozoic. But you can see in each of these particular periods, they're separated by events that are generally global. The geological community knows these particular features and they can identify them throughout different continents on Earth. You'll also notice that many different species were dominant over time. And I don't see too many humans here yet in this particular plot. Also, these particular periods were dominated by periods of extinction. Many of them are quite well known. There are 5 during the Phanerozoic period, and my apologies, and many of you will know them. But where are we? We're down here, this little tiny dot somewhere in the Quaternary. And that's now considered to be a new geological epoch. Let's look at that epoch. The Holocene, which is the recent period, and now what's called the Anthropocene. These are ages that you will know of from your studies in history, probably in 8th grade or so, I suppose, in primary school. And there's 10,000 years here, and what you see on this plot is the population change over time. The marker here for the Anthropocene is roughly at around about the year 1800, which is about the time the Industrial Revolution seriously got underway. The difficulty with marking it at this point for some people is that in fact the Industrial Revolution wasn't worldwide. It began in the UK and Europe, and over time, over many centuries, transferred to other parts of the world. But in a million years' time, geologists of the day will not worry too much whether the marker was at 1800 or 1942 or 1946. Within an order of magnitude, it's about here. Now, it's difficult to see. This is an exponential curve, and I've only got this out to the year 2000. There's another 14 years worth from here. And it's often difficult for people to understand what that rate of change actually means. So with a bit of luck, I'm going to actually take the opportunity to show you what that means. It's worth just contemplating that. Current world population, taking into account births and deaths, and you'll notice that the top populated countries, Indonesia's fourth, Brazil, and so on. Now, some people, when they look at that, and they think, oh my word, in 2050 we'll be 9 billion? How are we going to handle this? Part of the angst behind that statement is that people believe that we'll just be the same and behaving the same in 2050 as we do today. Well, I will put it to you that we won't, because there are other sorts of factors that will mitigate against that type of business as usual. In other words, we will not be treating the environment the same way in 50 years' time or even 30 years' time. We will not have the same economies as we do now, and so on. And what I want to get back to now is to indicate how those economies will change. Ah, Dave. Got it. This exponential plot, exponential curve, is common in the biological world. It's also common in the technological world. And many people who are ecologists and biologists will know that animal and plant life often takes an explosive increase in population, and of course also those species die off when the conditions are not quite right. The technology revolutions, and this is a plot from a McKinsey study, suggests that, in fact, if you actually plotted this out across the full axis, that this is the beginning of a technology curve that's equally as exponential. And some of you will already recognise what that is. If we look at this particular beastie here, just a simple iPhone, the computational capacity in this iPhone is equivalent to the best supercomputer that was operating in 1975, and it cost $5 million in those days. So $500, $5 million, and we know then that that's the known and commonly talked about feature of our modern day computer industry and the chip industry. But another thing that's worth mentioning, and we'll learn about this a bit further on, is that there's also not just an efficiency in the amount of memory storage and an efficiency in the number of computations per square metre of chip, but also an efficiency in energy. The cost of energy to have driven this sort of capability in 1975 and the amount of energy required is substantially different to what's required now. So we've become clever not just at chip making, but also at cooling things, understanding heating, understanding thermal properties. And it's these sorts of revolutions that I believe will allow us to adjust and accommodate to the challenges ahead of us. Because not only will the technology revolution be an exponential path, but many of the subsets of that will be exponential. And our understanding and our political environment will need to follow suit, as well as economic. I want to bring you back in time just one moment, because we've had two plots just before that, one of 12,000 years approximately and one of 2,000 years approximately. And what we now see here is one of the major forcing features, longer-term forcing features in the climate of the Earth. And this is a timescale from 0, that's present, to 600,000 years ago. And these are various parameters that are used to measure the climate of the time, and many of you will see that this is the glacial, interglacial periods that have occurred over that 600,000 year period. Sea level changes from 0 to 100 and 0 to minus 100. But I'll point out here, that is 10,000 years. And that's 2,000 years. So double that, and virtually the whole printed, or the whole documented civilization of humankind takes up that amount of time. So the scales we're talking about, that of human knowledge and of human existence, are very, very different to those that are in the geological world. But also you'll note that some of these features, some of these changes are dramatic over that period of time, almost exponential. And it's this sort of thing that concerns many climate scientists today. So the primary drivers, the natural ones for climate, can be broken down into three basic types. Of course, the sun, the solar radiation, it obviously has the major impact upon the Earth and is what causes those, or what you'd call short-term, feedback mechanisms, the change of seasons, the night and day, etc., etc. There's longer-term timescales of tectonic and landmass distribution in the order of millennia, and then there's this orbital forcing, which is quite a number of different types of timescales that influence what you would call, on a slow feedback mechanism, the types of climate that we have on Earth. And this sort of orbital forcing depends upon, in fact, just the wobbles of Earth around its axis and its relationship to the sun. And one of the things that is concerning climate scientists right now, and particularly James Hansen, is just exactly what are those slow feedback mechanisms that are influencing the globe that we haven't actually put into the climate models up till now. And it's quite reasonable to have thought about that at this time, because up till now, some of those feedback mechanisms have not actually been dominant. Let me give you an example. Most of the models to date have been based upon the past 100-year history, and they've not included, for example, the fact that ice sheets are unstable. They were quite stable for the past 100 years, but it's only now that they're starting to become unstable. And there's the potential that, in fact, the disintegration of the Antarctic and the Greenland ice sheets could well be exponential. So that's something that's concerning people. Something's wrong with this. Sorry. There we go. Now there's a group in Germany that have done a bit of a retrospective study, on the risk factors for different parts of the globe for climate. And it's taken into account many factors, not just the actual event itself, but also social capacity to respond, resilience, and other sorts of features that are much more demographic oriented. But if you look at this plot, you'll see that this particular area of the world is at high risk based upon previous data of continuing climate change. So is Australia, but nowhere near as much as Mongolia and India. And this happens to be the area where there's in the order of 2.5 billion or more people on the planet. Also, even though this is a fairly low set of indices here, within Africa there's about 1.2 billion people, and it's projected that Africa will be the fastest growing continent on the globe over the next 30 years. So they may well also be subject to some climate risk of some significance in the future. This outfit has actually started to now record meteorological events and make an assessment, or an assessment of confidence that the particular event is attributed to climate change. There are three here I'd like to highlight. Each of them have a high confidence that they would be attributed to climate change. You recall the hot summer in Europe in 2003 resulted in deaths of about 70,000. Another one in Texas in more recent times, which is also a drought. And again here in the Eastern Mediterranean, And these are talking about dryness and drought of that sort. The other ones, lower probability, of course, in Victoria, is one that we know well. And if we have a chance, I'll talk a little bit about the unintended consequences of renewable energy in that particular region. So why is climate important? Put simply, all species live within a particular temperature range, from about 5 degrees to 40 degrees. We can sometimes tolerate much higher temperatures and levels of humidity, not always, but most species have a comfort zone here, and that comfort zone is a zone where we really don't need to have a built environment or an additional environment to be comfortable in it. There are, of course, extreme beasts and bugs, mostly in the microbiological world, that can handle much higher temperatures and much lower temperatures, and these are known as extremophiles, or they can live in anoxic environments. But these are not the sorts of things that we're interested in at the moment, because the main reason for climate being important is because we and our plants and our animals require this temperature range to operate. And the other reason it's rather important, and I just think it's worth looking at this, and the purists amongst you will forgive me for using this approach to comparing nature. It's not quite correct, but it's good enough to give you an idea. Basically, an hour of solar radiation is around about 5 orders of magnitude larger than anything that man can generate in the same time frame. A tropical cyclone generates a significant amount of energy per day over 2 or 3 days. No wonder it causes damage. And that cyclone occurs because it's re-equilibrating energy and redistributing energy across the planet. The atmosphere and the oceans are the two major conveyors of heat or energy across the planet, and it's those disturbances or that disequilibrium that causes these disturbances. And you can see here the Gulf Stream. Some of you will know that it's also a particularly powerful stream and generator of heat to northern and western Europe, 500 times the scale of the Amazon River, and therefore nature itself has significant embedded energy in its operation. I'll give you some brief data now on update on data that's just recently come out. This is from the Bureau of Met and CSIRO, and it's going back to what I was mentioning earlier, that on timescales of decades, this is from 1951 through to 2013, these are plotting monthly average temperatures that are warmer than usual and cooler than usual. And you can see here that over that period from 1950, the number of warmer days on average has increased from 2.2% to 10%, and the most recent over the past 15 years. So we're getting more and more longer days of warmth and hot temperatures. By the same token, the number of cooler days has also decreased from 1.7% to 1%. Where's this heat going? Well, it's going into the atmosphere, it's going into the surface parts of the planet, but it's also going significantly into the ocean. And this also is another factor that builds into this issue of slow response, slow feedback mechanisms that are on the planet. These are data taken from 1960 through to 2015, I think, yes, which show that the oceans are gaining heat over time and at a significant rate. What we don't know is how much heat these oceans can take, and of course, what influence that has on the chemistry within the oceans. We know it has an influence. If you raise the temperature, of course, CO2 can't go in there as well. Right? It doesn't dissolve as well. And so these are particularly important questions that climate scientists are currently addressing. And in particular, James Hansen has been doing some very interesting work there, and I'd advise you to look at that paper if you can. It's just recently out in PLOS One and would give you a much more detailed analysis of this particular situation than I can give. So there's lots of statistics about this whole exercise, the demographics of climate and climate itself. Just point out a few, I won't go through them all, but the water table in Beijing has dropped 300 metres since 1990. That's an interesting observation. 75% of marine species have shifted their range poleward by as much as 1,000 kilometres. The local fishermen around here would know this. and the decadal average isotherms are moving poleward at a significant rate since 1980. Another one that we'll get a chance to look at in a moment is that the USA, however, has reduced its greenhouse gas emissions by 12% in a very short period of time. So, So this is another plot from James Hansen's work, and it just documents for the US, although he's also done the same sort of plot for the globe as a whole. The data for the US is just more detailed and accurate, which points out that the amount of energy usage by source over this period from 1850 to 2012. And this is again putting things into context to understand that prior to the Industrial Revolution, one of the major sources of energy was actually wood, and wood in particular. And that was okay whilst it was possible to regrow those forests and then reuse the wood, but that's not been happening for quite some time. The forests are being taken away at a far greater rate than they're being replenished. So that starts to worry people as well. And as you can see, coal usage peaked significantly in the early 1900s, and as a proportion has been taken over by oil and gas and other products. And this points out, I make this point because energy consumption generally is one of the major contributors to greenhouse gases. There are other contributors, but it's the bulk of most westernised countries in particular. So let's look at electricity generation and what's the difference between different forms of generating electricity. Well, as we can see, the amount of greenhouse gases emitted by coal and lignite is significant. Natural gas, much lower. And then you have what are called the renewable energy forms here. Very low in greenhouse gas production, sometimes very inefficient, sometimes very efficient. And it's this sort of trend, this change from the more greenhouse gas emitting types of electricity generation methods to these that is actually now documentable in the history of a number of different Western societies. And I'd just like to point out that whilst there are proponents of one that say, well, renewables and we've only got to do renewables, and others say we've only got to do oil or only got to do coal, you know, there is a halfway house. You could put hybrids in place. You could have some capability of using biomass or nuclear or solar PV and marry it with these sorts of technologies that can provide you with the base load or the peaking power that's required. Now, I just want to then point out that there are some unintended consequences of the energy generation exercise that's happened over the past few years, and it's something that is worth noting. In 2012, the world's total greenhouse gas equivalents went up significantly. Other countries as well. However, the United States and the European Union showed a decline in the amount of CO2 emitted through energy generation. How did that happen? Well, the drivers have been happening in the US for the past few years, and fundamentally it relates to three basic things. In this period of 2009, when the per capita output was decreasing significantly, and here as well, this is the result of economic conditions, the post-GFC crisis. People were not doing things, not demanding as much of their energy. But in addition, in 2012, there was also a difference in demand, nowhere near as high as it should have been, because at the same time, it was a relatively warm winter that particular year. Now, these green and yellow bars are result of another factor that's been very important and has been occurring from about 2006 onwards, and that is that coal-fired power plants in the US have been converted to gas-fired power plants. And as a result of that, you will tell from the previous slide that that has changed the greenhouse gas budget significantly when you put replace coal-fired power plants with gas-firing capability. And that could only occur because the shale gas revolution in the US, which Peter McCabe talked about last year in the Grand Challenge lectures, has actually allowed that market to be almost self-sustaining, the price of gas went down significantly, went down so low that it was actually cheaper than coal. Cheaper to put gas in the power station than coal. And then, so an economic condition converted, and of course the demand was not there. They didn't need to run some of those power plants, so as a result of that, you end up with economic conditions that have shifted the US to being a significantly lower emitter of carbon greenhouse gases than previously. That's a major achievement, and that came about because of circumstances predominantly in the US, but likely to be carried out in other parts of the world in the future. So the challenge. Pretty stiff challenges. We need to, pundits say that we need to increase food production and usable water and energy capacity by 2030 to these targets. Can we do it? Well, a couple of different ways. We can do it if we innovate, we collaborate, and we make a commitment to it. And fundamentally, you will have heard a very inspiring talk last year by Jeff Garrett on innovation and the many different ways we can innovate within our community. And I think we don't need to spend a lot of time about that, but a lot of that innovation will come about through technological change, because that's what drives many of the economic systems within on our planet. But in addition, there needs to be significant cultural and social change and understanding of social capital with innovation. Why do we need to eradicate poverty? Well, it's rather important because nations or communities that are confronted with challenges have a much better chance of being resilient and surviving those challenges if there are fewer people who are in poverty. This is a fairly well-defined matter known by many around the world. We also need to extend education and literacy, and in particular science communication. And I think in a couple of weeks' time we have the director of RI Oz coming to talk about that very thing in the future. So, can we change the world? Is it a collective effort? Do we do it all together? Do we do it one by one? Do we rely just on one or two people? And have we got evidence, for example, that people have changed the world in the past? Well, luckily, there are a couple of people in our community who've been looking at this particular issue. And next week, we'll have providing us with one view by Peter Andrews, a commentary about what he calls uberpreneurs. These are people who are super entrepreneurs, who have changed the world. And it's not surprising that there are quite a lot of them. Some of them are household names, some of them are not. And in fact, it will be very informative to understand what both Peter and Fiona think about what is it that made those uberpreneurs. Is it nature or nurture? And ask him that question when you're here next week, because he'll be able to give you a very succinct answer. There are other ways that individuals can make a difference, and this is one good example of a person, very famous scientist and engineer and designer of quite strong repute. He calls himself Trimtab, Buckminster Fuller. Sufficiently well known that a carbon molecule has been named after him. What's a Trimtab? Well, it's a small surface connected to the trailing edge of a larger control surface, for example on a boat or an aircraft. Duncan will understand what I'm talking about here. It's used to control and to counteract the hydrodynamic or aerodynamic forces of a boat or an aircraft as it's going through a particular medium. And what it means is that you don't have to apply a lot of force. You just touch it here, touch it there, and you'll change the direction of the cruise ship or the plane and so on. And Buckminster Fuller believed that he was a Trimtab, but he changed the world as well. And his implication, of course, is that we as individuals can all do that at the same time. Now, what about collaboration and collective groups, nations, countries, meeting big challenges? Well, yes, it happens. And I'll go through one or two of these. You've probably, a number of you will have heard me go on ad nauseum about the stunning engineering, science and technology advances of landing on the moon, the International Space Station, and nowadays in modern parlance, the Square Kilometre Array. So I won't talk about those, but I will talk about one here, a small country in area, large in population, about 120 million, I think, is Bangladesh's population. They have, they're on the delta of a major set of river systems. The Ganges feeds into that area. Its elevation maximum is 5 metres above sea level. So naturally, with all of these rivers taking the mountain melts from the Himalayas, it's subject to flooding on a very regular basis. It also has, on occasions, severe cyclones at the same time as those monsoons and the flooding occurs. And in 1970, there were 300,000 deaths as a result of that. The same strength cyclone, 138,000 in 91, and only 3,500 in 2007. So what did this country do to make a difference there, to meet that challenge? Well, three simple things. The first thing it did, put in place a reasonably accurate meteorological service that could forecast what these cyclones were doing, could track them, understand where they were going. Second thing, they advised the population to start to build safe houses or places where they could lift their stuff up from the floodwaters on a regular basis and just store them during the time it was on. And then thirdly, appropriate to the technology and the community at large, when a cyclone was predicted, they would get their population, the designated people, to jump on a bike and cycle around the country and tell the population, a cyclone's coming, get ready. And that's all they did. They met that challenge head on. I'd now like to talk about the Montreal Protocol, which is another example that global challenges can be met. This is one that began, the protocol was signed, I won't go through all the detail, but it was signed in 1989. It's undergone 7 revisions. It's considered the single most successful international treaty that's been put in place in modern time. It's been ratified by 197 parties through that period. It started out with 20, 197 now are signing it and committed to it. And basically it's in order to ensure that CFCs, chlorinated fluorocarbons, are not that can damage the ozone layer are not in the atmosphere and not used and not produced. And as a result of that, being put in place since about 1989, you can see here that the overall CFCs is dropping precipitously, 10% from the peak around about 95, 96. And this is an example of the ozone layer taken from NASA, showing it at one of its maximum extents in the past. So this also shows you that you can get communities together. And in this particular case, the developing nations never did produce CFCs, but they might want to use them. So this treaty allows for developing nations to be supported by the developed nations to actually ensure that alternatives to CFCs could be used in their community or in their industry. A signal success. So, what other policies and practices have been done, have been carried out, and can people do things quickly? Yes, they can, because there's a bit of urgency coming from the scientific community about the need to change some of our practices. So, is there evidence of that in the past? Well, yes, there is. 2011, from 2001 to 2011, Germany increased its non-hydro renewable energy from whatever it is, 4% to 19%, a major jump. France increased its nuclear proportion of electricity from 8% to 70%. Massive. Countries can do it. They can change. And you'll notice that some of the developing nations are very much jumping the hurdle and not going through the Industrial Revolution, they're going through the Green Revolution. Bhutan has committed 60% of its landmass to forest for all time. And, for example, you can see here that another one, this is a UN initiative, but the reduction in extreme poverty over the past 20 or so years has been 50%. That's a significant change and a major shift for people. So people can do it. But what are we doing? I think this direct action. This is where the private sector is making a difference. These are just recent comments and news articles from the local over the past month or two. Here's another example. The Climate Council now is an independent, non-profit organisation designed to provide clear, easy-to-understand facts on climate change. How did that happen? Well, the federal government said we're not going to have a climate commission. Within a week, they did a crowdsource, raised $1 million, now operational. So people are doing things. Private sector's doing things. And I can't finish this without talking briefly about the bioeconomy, how important that will be to the globe in the future. I believe the major impact will be in chemical products and chemical products sourced from biological biomass itself. And this is an example of the sort of concepts that are related to the development of a biorefinery. And at the moment, that particular industry is worth a couple of billion and predicted to go up significantly as a proportion of the chemicals industry around the globe. And that will make a significant difference to our greenhouse gas budget at that time. So let's turn to the future. There are lots of pundits on the future, and some of them are famous, and one of our more famous alumni, James Moody, put this together about while he was at CSIRO, and he wrote this book called The Sixth Wave, which describes the future as the convergence, for example, of the digital and the natural world, a world where there's limited resources. That's implicit in what I'm saying, that there will be more of a personal touch to products and services and so on. And that sixth wave is the follow-on from the other 5 waves that preceded, and most of them would have started in many countries such as Western Europe, and to some extent Australia. We probably started around about here. Each of these countries have gone through these sorts of waves. And again, a disruptive technology in the very early days was the steam engine. But it's interesting that many of the developing nations that were at this summit in Delhi were saying, it's not for us, we're going on into the sixth wave, we're going to develop the green economy. They see an opportunity for themselves to build a strong, resilient economy through doing initiatives that are going to reduce the burden on our greenhouse gases. And indeed, some of these thoughts were what were behind the original concepts when the research leadership got together a couple of years back to talk about the Institute for Future Environments, where we believe that the research opportunities were at the intersections of these 3 basic environments. And of course, we delivered and derived out of that a number of research themes. And I just let you know that over the next couple of months, we'll be evaluating those research themes as well to see if we can fine-tune them, hone them down to get them to be much more precise and matching the sorts of skill sets that we have at QUT. Other futurists talk in terms of physics. This guy's a chap that will be visiting us soon, and he's spent quite a lot of time evaluating what's called Star Trek science or science fiction. And many of you will know that one of the more famous science fiction writers ended up becoming an advisor to NASA, because back in the 1940s he wrote a science fiction novel about these things that would rotate and orbit around the Earth and communicate with people on Earth, eventually called satellites. His name was Arthur C. Clarke, and he wrote quite a number of very good science fiction books. If you have a chance to read them, you'll enjoy them. But this chappie is more recent and modern day, and he's got a series of impossibilities, and this particular class is just simply those things that haven't happened yet but are not contravening the laws of physics. I don't have time to go through all of them, but fundamentally these sorts of things are actually either in train or happening. And of course you will know that we have a significant cohort of people working on developing robot vision that implies conscious and emotional, eventual robots. And you will have heard Peter Corks talk about this sometime in the middle of last year. But it fundamentally boils down to exploration and exploitation of new materials. But these sorts of things are likely to happen. And they're not going to happen at an incremental pace. Going back to the original comments that I made at the beginning, many of these changes will occur at an exponential pace. And those exponential changes in technology and capability will be in effect, the way in which we will meet the challenges, particularly related to climate change in the future. Make sure you go. McKinsey again. They've written an interesting report about disruptive technologies that will occur in 2025, and they've done a bit of a weighting here where they've actually weighted it according to not just the capacity to disrupt, but also on its economic impact. And because they reason that this will drive new businesses, it develops different economic models and eventually will arise significant changes in the way we consume energy and care for the natural environment. What they've done is worked out the relative impact here for developed countries and for developing countries. And you'll see that down here renewable energy has major impact for developing nations, not so much for current. Up here, the mobile internet, 50-50. And the outcomes, well, here's a good one, that the cost of doing a human genome sequence will be $100 in 1 hour. Some people down at the Garvan Institute reckon they'll do that by about 2020 or 2018, I think is the number at the moment. So the pace of change is dramatic, but we can be beneficiaries of this if we can put it to good use and harness it. And I'll just point out that QUT happens to have a pretty good play in many of these spaces. Not too bad in the world of advanced robotics, autonomous vehicles. We've been there, we're in that space, and these are the sorts of areas that we believe QUT will have a significant contribution to make in the future. Oh, there you go. QUT, what's it going to do? Well, I think it needs to be excellent at key technologies that change the world. It also needs to be proficient at interdisciplinarity. And it's based upon disciplinary strengths. And it needs to align itself with real-world outcomes. That's not a surprise to most people who live and work in QUT. I think that's where we're going. And that will be able to generate, I think, many benefits for not only this university, the region, the nation, and the world, and the universe. I'll now talk about a couple of very examples. I've only got 2 simple examples of this, and since we've been talking about energy a bit, I'll mention 2 projects that have been going on. Most of you will know about the major achievements over the past year or so, the Centres of Excellence in Big Data and Maths, and the Centre of Excellence in Robotics. So I won't go through that, but I'll talk about some smaller scale projects that are seeding and that might show benefits in terms of energy as we go forward. This is a relationship between Ergon Energy, QUT and Smart Grid Partners. And you know, it's simple, it's very low tech, but if you instrument roofs and you put a coat of paint on it, you'll be able to find out that whether you can improve the energy budget for that particular location. And here's an example. The school roof temperatures, these are before the roof was painted, very high, and after it's painted, around about 35. So there's in the order of a 10 to 15 degree difference in the roof temperature just by coating it with the right sort of paint. And the same thing here. This is now the energy draw, in other words, what the air conditioning requirements would be in that building. And in general, 10 to 15% reduction in demand occurs by doing something. That's being done by QUT, and that's now being rolled out to quite a number of schools around Queensland, and a number of other businesses within southeast Queensland are very actively involved in this sort of work. Just because most of you will be saying, yeah, Townsville, well, it's hot up there, it's got to only work in Townsville. Well, not quite. Here's an example a little bit closer to home where the same sort of impact has occurred. So that's a simple, low-tech example of the sort of things that's going on at QUT that make a difference. Finally, I'll just mention something that's quite different. It's not often that the people at QUT work extremely closely with energy companies, and many people would believe that energy companies over the past decades or more have not been the best stewards of our environment. I think that would be a fairly reasonable statement. And they know that. So when they start out on new projects now, they're willing to adhere to contractual obligations that require them to take strict notice of environmental conditions. This is a circumstance in Barrow Island. You know Chevron is developing an LNG processing plant out of the Gorgon field, taking gas from there. And this is the beginnings of that particular LNG plant being put on Barrow Island. Now, there was an earlier piece of work done by our statisticians here at QUT to evaluate what would be the biosecurity risks on that particular island. And subsequently, over the many years, we've worked out that indeed it can be done if you put constraints. And the constraints are that nothing can go on or off the island unless it's been strictly quarantined. In other words, every single bit of soil, tiny little bug, a leaf, chewing gum, whatever, has to not be on the island so that the natural biodiversity is retained throughout the life of that plant. The problem Chevron has, it's got to train its quarantine inspectors. It has a couple of hundred, and everything goes through the Perth airport. That's the only advantage they've got. Everything that goes to Barrow Island goes through the Perth airport. But they've got to train a couple of hundred quarantine inspectors to work out how to do this properly, and they've also got to know that they've learnt to do it properly. So what they've done is they've come together with us and another company, small company called Bondi Labs, to work out and develop a simulation game, or what's called serious games in some quarters, others call it educational game, so that we can actually immerse these trainees in a quarantine environment, teach them how to do quarantine inspections, and then assess whether they've actually met that standard or not. This is a simple example of how QUT's technological skills can help an energy company meet its environmental obligations. And there are many other examples that we have going on throughout the university. So, to finish off, we know that the Earth's climate is driven by energy imbalances. To understand it better, to know more about the deep ocean as well as the shallow regions of the ocean is very important to increase our monitoring and reporting. It's important to understand those fast and slow feedback mechanisms because we really don't know how they are going to work in the future models that are being developed. And we need to learn how to adapt. And I would say to you that history has shown us that we have very innovative people, very innovative entrepreneurs, very innovative communities that can actually meet challenges and deliver on the outcomes. And those challenges are not beyond humankind. Sometimes these changes will be exponential, but I think we can use them to our advantage. And then for future generations to come, we really need to have visionary and committed individuals now within this place and in the future, and train our individuals and students to become visionary and committed, and of course to innovate exponentially.